reminders. These first few slides are just reminders and allow you the opportunity to raise questions. So we were comparing an undulator at a synchrotron facility where the undulator itself, the magnet structure, has a period of a few centimeters, like 3 centimeters typically, but it could be 8 or more. And an electron bunch that comes through, which is a little bit fat. In fact, it's highly elliptical. And the electrons, maybe 10 to the 8th or so, maybe 10, close to 10 to the 9th in some cases, where the electrons are moving around randomly. There's complete chaos there, okay? And that's to be compared, and this is the equation of motion, the momentum equation, where this is the Lorentz force, and the main force, in fact, this the momentum P is going to be gamma mv, where m is the rest mass, gamma is the entering gamma, and the V cross B is the dominant force. The electric field plays no role, okay? And then when we go to evolve towards the free electron laser, it's much longer. The electron beam laterally is smaller and small enough to satisfy our coherence condition. And there's more electrons in the bunch, in each bunch, so that the current is higher, actually, okay? And that gives us more electrons radiating. And, okay, and the momentum equation, the rate of change of momentum, now has to include the electric field, but because it turns out the radiation is becoming so strong in this long undulator, and because it's coherent, the electric fields are adding in phase for all of the electrons in this bunch, okay, or large number of them, let's say, are adding in phase. And so we're getting a really big multiplier on the electric field and therefore on the intensity, which gets squared, okay? So in the beginning of the undulator, of the free electron laser, which compared to the synchrotron, which was a few meters, it's going to have the same period roughly. Could also have a 3 centimeter period, but it's going to have a length which is of order a kilometer. Actually, the magnetic length won't be so long. You'll see numbers later. It'd be more like 1/10 of that, okay? But early in the process of this electron bunch, when it's first coming through, there's just random fluctuations. And of the 10 to the 8th or 10 to the 9th electrons, some bunch of them somewhere in the bunch, front, backs, form what appears to be a modulation at the wavelength of interest. And if that happens, or when it happens, it comes out of the noise, then that starts leading to an amplification process. That's the next slide. And eventually the modulation starts to grow and reaches saturation, okay? So these are the 3 things it requires in order to get an FEL out of it. Much longer undulator, higher peak current, smaller electron beam for better coherence. Did anyone want to say anything now?
Sorry, so I understand what you're saying about how, the undulator, a normal undulator is shorter, and we have more sort of random electron orientation. But so is it that since the FEL is like, I guess I'm confused because you mentioned like SSRL has an FEL, so it's like drawing off of undulator radiation, or is it that it's like an FEL can also be like separate from an undulator? Like, does it need?
No. The undulator, yeah, good. Good to ask questions like that, Neil. No, the FEL is this long periodic magnet structure is the FEL. It needs an electron beam injected into it, and eventually the electron bunch will move through this long undulator, and some modulation will grow exponentially. But this long magnet structure and that beam of electrons, modulated beam of electrons, that is the FEL. Okay. The only other thing is it's in a long tunnel. The synchrotrons were n-sided polygons, right? But this one is just linear. In fact, that's where the name for the Stanford one comes from, linear coherent light source. Yeah, great. Okay, yeah, I'm sorry, go.
I remember you saying last week that people were shocked when the first FELs reached those really high energies.
Yeah.
Um, what what made that so surprising? Like what technical advance was unexpected that led to that?
Well, so I actually have a slide on this later, but in short order, the you only get lasing if the beam, the X-ray beam, and the electron bunch are overlapping each other, close to perfect, and they need to do that for actually a propagation path which is greater than a kilometer. So you've got a beam size that's sort of 100 microns, and you want these two things to overlap each other for a kilometer. For me, that was what I found so startling. I had been on their advisory committee early on, so I knew what was coming and I knew how well they were doing with all kinds of things, but I still found that the alignment would be such a bear. And to do it, at these X-ray wavelengths, as I mentioned, we were already shocked with the EUV laser in Hamburg called Flash, but that was a shock because the wavelength was so short, now even shorter. So anyway, I'll put some numbers together in a moment. You see, you're talking about nanoradians of alignment, and how SLAC aligned and how SAKLA in Japan aligned completely different. So quite interesting. One of the things you can do is I show this long magnet structure, but actually there are, I don't know, 40 or so segments of a certain number of magnets. So there's a whole bunch of these magnet structures. I wonder if I know. Well, we'll see it in a slide later. That they're all 3 or 5 meters long, but the magnetic length is like 100 meters. And so there's a lot of them. As I have the sense that it comes out to something like 50 of them. And so what they do is they put them in and they jiggle things around a little bit and get the best amplification out of it. And once they've got it, it's stable, it's fixed, which is another amazing thing, that everything was so stable. And they not only got it, in fact, you'll see in a moment, they actually got it the first night. It's totally impossible.
And that alignment is harder to do at the higher energies because the wavelength is so much shorter.
I thought.
That makes sense.
Yeah. I have to think about why I thought. Was there a reason? Was there a real reason to think that, or it just seemed shocking? Right? Yeah, we'll show something too when we get to SAKLA about the sizes of the beam. Here I said the radiation cone, central radiation cone, 1 over gamma square root of n. And so for the synchrotron undulators, they were like a few tens of microradians. And here they're going to get down to a microradian or half a microradian. Okay, so
Professor?
Yeah.
So you mentioned that as our beam travels down the path, it becomes fully modulated and saturated. Is there like a threshold we've established for defining those terms?
I'll show you the curves in a moment, experimental curve, you'll see. But here, in this slide here, you sort of get the idea. But there are things that happen when you approach saturation. So you could define something here. So you start in the beginning with a completely random electron distribution. And when this somehow or other, statistically, a small short wave appears somewhere in here, and we start to get this feedback mechanism with the electric field pushing the electrons into little micro bunching. And so we get a partial ordering. And then it goes up. And by the way, to get this ordering, energy has got to come from the electrons to the photons. So there's an electron transfer here from the beam electrons to the radiation. Has to be, right? Conservation of energy. But it's a pretty substantial thing. And as you get up to saturation, where it's so beautifully modulated, you'll find out that it's taking a lot of electrons a lot of energy from the electrons, and gamma is no longer a constant. And so if gamma is not a constant, if there's a spread of gammas, delta gamma over gamma of order 10 to the minus 4, actually, I think it's much less than that. It's more like a few 10 to the minus 3, a few 10 to the minus 4. what happens with that electron energy spread is because of different gammas, you're radiating different wavelengths. So there's a point, I'm showing this thing saturating, and in the imaginary people I had running this experiment, they turned everything off at 140 meters, okay? But if they continued, this thing would roll over. So, and it would roll over, among other things, because of the spread in gamma, the spread in energy of the electrons, because not all electrons gave up the same amount of energy. And it's going to make this thing roll over, and it kind of oscillates and decays. So you can figure out, you could make a definition from that, but usually people look to get something, certain power level or something like that. Whoops, did I go the wrong way? I did. Okay, so this slide was important because it shows that here's our imaginary little wave that started out of noise for a certain number of cycles, and it involves some number of electrons. And this is showing this wave shown both here and here moving along with the electrons. And so this only has, this is the scale here is one magnet period, right? That's one oscillation. And this is a few hundred cycles at around a nanometer or less than a nanometer. So this is a few tens of nanometers, maybe 100 nanometers, but it's not very long. Okay, but it has a lot of cycles, several hundred. I think typically 500 cycles, could be more or less. But for electrons that happen to be, so there's a bunch of electrons here. For the electrons that happen to be lined up with the electric field of our little imaginary or just prototype wave that's just starting, for the ones that are lined up with the positive electric field at its peak, they get electric field kick in the Lorentz force. And for those electrons, because of the kick, they go off axis a little further and they're a little slower to come back. It takes them a little longer to get back. And so there are some electrons that were located here at the peak of this pulse that would have arrived here, but they arrived here. So there's going to be less electrons here and more someplace else, okay? And likewise, a half cycle behind, for the electrons in the bunch that were here, they got a kick in the opposite direction. They come back to the axis early. So again, there's a depletion of electrons where there would have been a crossing, and there's going to be an increase a little distance away. And this is the difference between these two is a half wavelength. This difference is not a big distance. The whole thing is going to produce a micro bunch that has a wavelength, has an X-ray wavelength. Does anyone want to say anything? Okay, so there has to be energy transfer. You know, if you start from chaos, you can't start from chaos and get to something orderly without doing something. You have to give it energy, and you have to have a mechanism. So this is the mechanism, and this is the rate of change of energy. This is the energy equation, and it depends on this V dot E. So it has to be a place where the electron has a component of velocity going up, and there's an electric field there, okay? And the dot product does it. So, okay, so that's an outline of how does this work physically? To go through the mathematics, we took a one-dimensional model, which gets us the basic operation of the FEL. It doesn't answer every question, but boy, it does a great job of answering many of the basic questions. You know, what is the gain length of this exponential process? What's the spectral bandwidth? How much power is going to be radiated? You get all of that out of this relatively simple model. You need to correct for several things, and we'll talk about what that is in a moment. But the equations that we have to worry about for this one-dimensional motion are the force equation, or the rate of change of momentum. We would call it the momentum equation. Classically, this would be F equals ma, and for those people involved in plasmas or fluid, this would be our momentum equation, okay? And we'd have different terms here with collisions and stuff like that. But these are the forces that matter here. And this time we keep the electric field. The rate of change of energy is this equation. And the velocity in an undulator, V, we figured out before. And that's what this is. Okay. So we're using our knowledge from the previous chapter with these definitions. And so those are two equations. We need a third equation because of the number of unknowns. And that is the one-dimensional wave equation. And to understand where this comes, and maybe the others also, for these two, you would have to read the chapter. I'm not saying that you have to do that. I just want you to understand how the analysis goes. The one-dimensional wave equation, you even have to go to an appendix at the end of the book. Okay. Oh, and theta is a phase angle between the position of the crest of the wave and the electrons. Okay, so some electrons will have a plus theta, and others will have a minus theta. There'll be a spread of electron positions to either side of the pulse. In fact, maybe I should have shown that here. This might be theta. This position here would be theta. We'll see it again in a moment. Anyway, there is three equations, momentum, energy, and the wave equation, which have to be combined. And we showed, at least didn't show, really outlined what the process was for reducing those three equations into a different set in terms of a position of the electron relative to the phase of the wave. That's what theta is. Eta was the relative energy, delta gamma over gamma, okay, and the electric fields. So we have three quantities and three unknowns. If you combine them, it's the only step that's easy. If you combine them, you get this third order equation for the electric field. And the E with the tilde on the top means that E is a complex quantity. So it could have growth or it could have decay. And that was our assumption from the beginning, that the electric field had the usual exponential minus I omega t minus k dot r. It had that usual for the phase variation, but also rather than have an amplitude E0, it had an EX with a tilde on top because it's complex. Anyway, so these three combine into a third order equation. And with all of these things all of these parameters coming together to give what's called the gain parameter. Actually, in the end, we're not going to use it so much. We're going to replace it with a gain length, something that means something to us in the lab. But you can solve this equation by assuming a wave of this form, that E sub x with the tilde it has some amplitude, and in e to the mu z, where mu, you just plug this in to this equation, and you'll find this relationship between mu and gamma. And if you take the cube root, you'll find it's a cubic equation. You're looking for three solutions. You take the cube root, and these are the three solutions, mu1, mu2, and mu3. This one is just an oscillation. It says mu is minus I gamma. So if you put that here, this is just an oscillating wave. There's no amplifier. This is not going to give an FEL out of it because it just gives an oscillation, right? These two also have oscillations because they have an I term, but one of them has a minus sign on the real part, and one has a plus sign. And when you put that in, the minus sign here is going to give a decaying wave. And this one with the positive sign is going to be a growing wave. So of the three solutions, one is just an oscillation, one's a decaying wave, one's a growing wave. Okay, and that's the one we're interested in. So if we put that in, we have then that our electric field, complex electric field, has this oscillatory part to it with Z, and it has an exponential growth. So you might, if this is electric field, we could say power is proportional to this squared, okay? And therefore, these things squared. But we're going to replace this by a gain length. And if you just do this, square this, and do this, you'll find that this gain length is shown here. So that says that the power is increasing as an exponential distance z over gain length. So it's a 1e folding for every bit of distance like this. Okay, so it depends on the undulator period, some constants here, and this row appears for the first time for us to see it, and it just came from all of these other parameters here. Whoops, what happened? It came from all of these things. You just track it through, and you'll find this is what everything looks like. Okay, and again, and so this is the gain length. It assumes it's a small amplitude analysis because we linearized our equation. So it's just giving us the gain length to get started. If you go too far, you have to switch to numerics. It has no 2D effects or 3D effects. And I'll mention to you in a while, what are some of the 2D effects that would make this 1D model a little optimistic, and actually will increase the gain length. When you start putting in some 2D effects, the gain length will not necessarily, it will take a little bit longer to exponentiate. The gain length will be a little bit longer in practice. So I'm just reminding you about the assumptions we made.
Professor?
Yeah.
When we're disregarding those other two solutions with the no decay or growth and also the one that's just decaying, are those not happening at all physically, or are they like also happening and it's just the growth one that leads to our FEL behavior? Like,
Yes.
what happens when we disregard those?
You know, you're absolutely, you've got it right there. They're all there at the beginning. They're all solutions of the equation. So physically, there's no reason for any of them not to exist. I would assume that all three do exist, but after a few gain lengths, the one of them is going to take over and dominate everything, and the others are just going to not matter anymore. So good question. Okay, so this is one I hadn't told you about yet, and this is about what is the spectral width? What is the relative spectral width for our FEL that goes through a certain number of oscillations, et cetera, and with an exponential growth? So just to jump ahead, this is the relative spectral width. And by the way, everybody understands, I think, that delta omega over omega is exactly equal to delta lambda over lambda for if you have enough cycles, right? So they're both the same, and I'll interchange them. But we're going to calculate here in a moment that the relative spectral width, in terms of full width at half max, is the same rho parameter with some numerical constant out in front of it, 3 point something. Okay, and we'll also do it for the RMS, and I'll tell you, I'll stop here in a moment because this is so commonly used. Okay? But anyway, so how do we get this thing? It's just a calculation, but it turns out it's an incredibly simple calculation. It comes from sort of an undergraduate Fourier transform or Laplace transform book. And so here's the model. Let me see if it has some of the parameters here. There's a wave, starts over here with some amplitude E0, and it's oscillating in time with a frequency omega 0. So that's going to be related to our undulator equation, etc. And an exponential gain. Here it is. Here's the exponential gain. This is for the electric field, so there's a 2 in here. The gain length was for power, or energy. Okay, so we have an oscillation that's growing in amplitude, and it goes so far and it ends. Okay, you get to the end of the undulator. And so the number of, so for instance, we commented before that the undulator equation for the FEL community, they leave the off-axis term, the gamma squared theta squared term. They leave it off because they're not interested in off-axis. There's no power off-axis. They're just looking at a really small angle, running along the axis. So this is the omega. This is just the undulator equation. Okay, it's just been flipped upside down in order to have an omega. Okay, and this is the gain length. Okay, and you can look up what is the Fourier if this is the electric field, what is the Fourier transform squared? And you'll get that it's a Lorentzian distribution around omega 0, around the central frequency, okay? And it has some width as indicated. And so the Lorentzian, you can just look this up in a book of Fourier transforms, and this is what you'd get for the Lorentzian spectral distribution, okay? And if you ask yourself for this thing, what is the full width at half max? It's this C over LG divided by these other things, the frequency, okay? And if you put them in, you find out, maybe surprisingly, that it's just equal to some constant times the FEL parameter. So the FEL parameter has popped up again. First it popped up in the gain length, and now it's popped up in the spectral width, and we'll see in a moment that's not the end of it. I like to put things, as you know, in full width at half max, but if you put it in terms of RMS, if delta omega was an RMS quantity, instead of this, you would have gotten this, roughly 1.5 rho FEL. And I tell you that because if you look at almost all of the accelerated papers, all the review papers and everything else, they don't show you this little analysis. In fact, when I showed many of my friends who have some of the original FEL papers that you could calculate the gain width this way, the response was, that's so simple, how could it be true? But it has to be true, okay? But anyway, if you put it in terms of sigma quantities, then the sigma for delta omega, the 1 over square root of E, you'd get roughly 1.5 times rho FEL. And if you look in the review papers, all of the early papers, they don't do this. They just say that this is approximately rho FEL. That's it. And they don't explain why it is. They just saw it in the simulations and they stopped there. Okay. So, of course, this is our one-dimensional model. So if there are various features might sort of spread the bandwidth a bit, you know, like your undulators are not quite aligned right, or so that gives a little shift to the angles. This would be. So anyway, typically they'll say that the beam width is roughly rho FEL, and they're talking about just an RMS quantity. They're not talking about full width at half max. They're just talking about this RMS width, okay? Okay. So these are the equations that we looked at. This FEL parameter pops up. We find that there's a lasing gain length, which is this, okay? We also find that in terms of RMS, there's a relative spectral width of, again, rho FEL. And what I didn't show you, but what one finds is that the saturated power, the peak power that you get out of this, how many gigawatts, depends on the number of electrons in the beam, or the energy of all the electrons in the beam. So each electron has an energy gamma m squared, and the peak current divided by E, that's going to tell us the number of electrons per second. So it's the energy, number of particles per second, multiplied by rho FEL, and you got the peak saturation power. So the fact that all of these things, all the analysis we just went through, came out first in a paper led by Claudio Pellegrini. You'll see the paper, it's Narducci, somebody, and Pellegrini. And it was a breakthrough paper. And if Claudio ever gets a Nobel Prize, that would be the start of it. It's where he got everyone's attention, okay? Also, the electron phase space, in order to have coherent radiation, remember I told you I would write it as d dot theta equals lambda over 2 pi, or I would say 2 sigma sigma prime equals lambda over 2 pi, but this is the way the accelerator people will write it. Okay. Any questions or comments? Okay, so what about this one-dimensional modeling? It's of course super valuable because it gives us a lot of insights as to what's going on. So one of the things, we have to have beam overlap to get this gain. So the propagating X-ray beam, which is like 100 microns in diameter, the X-ray beam, and the electron beam is like 100 microns in diameter, and they're going to propagate for a really long distance. And so if you took, let's take a criteria, just make up a criteria that you have to keep the two beams aligned, the photons and the electrons, to the diameter over 4. I'm just making up a criteria. And that has to be over a distance of 1 kilometer, because that's the spread of the undulators. It's true, I told you that the actual magnetic length was less than that by 1/10, but they're actually spread out further. There's some distance between the different insertable magnet structures. And so you need to maintain this alignment till you get out of the last undulator. And so this sets an angular tolerance of order 5 nanoradians. So this is one of the challenges that I thought would be startling. How are you going to manage that over? You can't align with a visible laser, to such an angle, because the visible laser, the wavelength's longer. So to have spatially coherent light from a laser, a visible laser light, which you would think, oh, I'm going to align with that. Actually, it's probably how you start. It's just a start. You need much better than that. Okay. And then there's also diffraction of radiation. So you have this 100 micron diameter, hopefully Gaussian or near Gaussian beam that's propagating out. And not all the radiation is on axis being amplified. There's clearly, if there's such a small object, there is clearly going to be some radiation off to the sides. That's lost power, and we did not include that. So in the numerical simulations, they would include that. And here's just it's an estimate of what kind of angle you would have for diffraction. It's not nanoradians, it's much larger, but this radiation is lost, and the FEL, the wave of interest, is being exponentially amplified as it goes along. So this loss out to the side turns out to be not so important, okay? But it is a loss. Now some of the things that went on. So the first, there had been lasing, I guess, up into the visible and slightly beyond the visible, but not very far, not very short wavelengths. And then the flash, so-called flash free electron laser in Hamburg, Germany came along. And this was the first major breakthrough. And that was in the year 2006. And this is if you've heard of coherent lensless imaging or coherent diffractive imaging, CDI, this was one of the first results that was presented, an experiment that was done with the flash FEL, and I think the wavelength was something like 109 nanometers. So that was a big breakthrough, and that was 2006. And then in 2010, actually the experiments were in April 2009, but the publication didn't come out right away because everyone was so busy. And so this is the first paper, and it was led by Paul Emma. And it's a really great paper to read. And as one of the things it says here, the lasing was done in April 2009, and it lased the first day. So what they did was they had this long path. It's more than 1 kilometer. I think it's almost 2 kilometers. And they have all these magnet structures, undulators, that they're going to push into the beam. So they start by just pushing in one, and they get some synchrotron radiation. and then they push in a little bit more, and a couple more and more, and they're just seeing a linear increase in the amount of intensity because there's no amplification at first. So the growth rate of intensity is just linear initially, okay? And the one thing that they're measuring is the beam diameter. They're having the radiation hit a fluorescent crystal, and they see the size of the beam. And as they put the first few undulator sections in, the size of the beam matches up pretty well to what we expect for an undulator at a synchrotron, 1 over gamma square root of n. And as n gets longer, this gets a little bit smaller, but that's more or less what they see. Okay. I could tell you some more stories, but maybe that's enough for now. So this is some pictures. I don't know how they were taken. This is Route 280 going from San Francisco down to San Jose, okay? And it was built at the same time as this LINAC was built, not for the free electron laser. It was built for high energy physics, but they were built at the same time so that the freeway would go over. The only thing that they built at the time was the little overpass section here. All of this stuff didn't exist. They just, in order to get this done and then not be disrupted later, they convinced, I guess, Caltrans to build a small section of the future freeway, okay? So this is what it looks like, okay? And this, I guess, is the freeway here. When you come over the overpass, when you come down 280 south and you get off at the overpass to go down Sand Hill Road to Slack, you can see this off to your right, this long LINAC, okay? Here's the guest house, and here's the main entranceway. This is Sand Hill Road. This is where the director's office is and many user meetings are. So in that paper, that first paper that I showed you a moment ago, this is some of the parameters. I'm going to summarize them again, but this is in their first paper, what they understood to be the case. And this is their gain curve. So who was it? Was it Andy or Angel who was asking what does the curve look like? And how do you know when you're at saturation? So this is the red are data points. And this is distance versus FEL power. And it's at 1.5 angstroms, about 8 keV. The peak current is 3 kiloamps. And one of the things I wanted to see. Okay, it's on an upcoming slide. Anyway, you can see this is the exponential gain, and they're getting up to around 10 to the 10th watts in a short pulse of around 10 femtoseconds or 20 femtoseconds, something like that. I think at the time they thought it was around 10. I'm not sure, but at any rate, around 10 femtoseconds, they've got this high powered, so 10 to the 10th watts. So a hard X-ray undulator, let's say at APS, would be about 10 watts. And this is 10 to the 10th. So they've gained 9 orders of magnitude in peak power. Okay, and this is a cross-sectional view of the photon beam seen with a YAG detector, a crystal. So it's X-rays in and light out on the other side, okay? And the measured gain length, it says, is 3.5 meters. Oh, here's something interesting. The undulators were, by the way, not tunable for many, many years. It's only recent that they've had some breakthrough, some progress on, some new work on that. The undulated period, what is this? Each of the magnet structures that they were inserting had a length of 3.4 meters. And there were 33 of these segments altogether. So you can multiply that, and that'll give you the total magnet length. But they got, and it's like 120, if you multiply these things, it's a little over 100 meters, 110 meters approximately. And what they showed was they got saturation in 60 meters, okay? Here's a summary that I made from their papers about the electron beam, the undulator, the photons, and the FEL parameters. So just let's look at this for a moment and then have maybe a discussion about this. The electron energy is 13.6 GeV, so gamma is really high, okay? Because don't forget, they're going to take an undulator period of 3 centimeters, much like the one at the ALS, but they're not trying to get 1 kilovolt, they're trying to get 8 kilovolt. So they need a higher value. And this is their current, and this is their rep rate. It's 120 hertz, and I misspoke or missaid what that was probably yesterday. But anyway, the repetition rate, how many pulses are coming, it's at 120 hertz, okay? The spread on the electron energies, the RMS spread, normalized RMS spread, is 10 to the minus 4. The beam size, sigma, multiplied by 2.35. So I guess I told you this before, but whenever the factor that converts from RMS to full width half max is this multiplying of 2.35. And the reason I put it there is so that I know I meant full width at half max, not RMS, okay? And so this is the beam size, roughly 50 microns wide, and the beam divergence, roughly half angle would be a microradian, okay? And the length, the longitudinal length of the beam is 21 microns. So there's every 120 hertz, an electron beam comes through, and a bunch of electrons comes through with about a 20 micron full width at half max, okay? These are the parameters for the undulator, the undulator period, the K value. How many periods are there altogether? So each insertable magnet structure's got 33 magnet periods, and there's 113 of these that get inserted. So the length of all the magnets is 112 meters, but they are spread out further so that the total length, which I don't think I have written down here anywhere, is over a kilometer. This is what was the photon performance. So the wavelength was 1.5 angstroms, 8 kilovolts. This is the photon flux. This is the energy per pulse. It's a millijoule per pulse. So that is a whopping number. This is a nominal operating pulse duration, 70 femtoseconds, but they, I think, very often operate more like 20. And the Sakla people in Japan, they always run at 10 femtoseconds, or at least it's their most common operation. And the relative spectral bandwidth, it says here 200 to 500. That's what they were observing. It's not, we had a formula, we developed a formula before which depended on some constant times the FEL parameter, and the constant was a number like 4. So our calculated 1D bandwidth would have led to lambda over delta lambda of something like 660. So our 1D model would have given a narrower pulse, 1 over 660 rather than this. But these are the kind of numbers that they were observing in the laboratory, okay? And there are some reasons why this is a little bit pessimistic, actually, because in the early measurements, there were reasons that the measurements weren't quite so accurate, I think. Okay, and then here are the FEL parameters. So for LCLS, operating with this electron beam, the FEL parameter is 1 over 2100. And if you look at the slides I posted the other day, I think this is slightly different. As I went through preparing for the lecture earlier today, I noticed a few inconsistencies. This was one of them. Okay, and if you take this P saturation, if you just, as Claudio Pellegrini and his co-authors would say, if you the saturated power would be about 25 gigawatts. slightly optimistic compared to what was actually measured. And this is the gain length, okay? And it reaches saturation at 60 meters, which is about half of the total path available. So they could have kept on going, and but they wouldn't have made things better. They would actually started to lose power, broaden spectrum, etc., because the gain curve rolls over and becomes ugly. But this becomes very interesting, as we'll see in a moment, I think today, when we talk about self-seeding. Okay. So this is a good place for a question or a comment. Just have any of you been used an FEL for an experiment? Okay, some of the people in Michael Zurch's group have used the FEL in Japan at SACLA, and they've had a proposal into LCLS. And there have been other people in the chemistry department who did PhD theses recently at the Italian FEL called Fermi. Okay, so things about spatial and temporal coherence properties of X-ray FELs. Oh yeah, so we were estimating that this is a single bunch, okay? They're coming at, we said, 120 hertz, they're coming through. They got a lot of electrons in them, and they could be starting early on in the long FEL, back at the beginning, these just statistically, different little areas start to produce waves which will eventually be amplified, okay? And so this is, we just saw a moment ago from where we were looking at the table of parameters, that this bunch length is around 21 microns full width at half Mach. So that's how long it is, okay? Each of these little bunches has a characteristic spectral bandwidth of, let's say, 500, okay, something like that. Our 1D model was that it was like 660, but more likely in the lab and by their measurements, it's more like 500. That means that each of these little electron waves, which is growing exponentially, they're all growing exponentially and separately, and they could all have slightly different frequencies, certainly different phases, but they're each growing, and they each can support 500 cycles, because that's the spectral width, okay, that we see. So these things can each have, each one of these could have a length. Each one of these little electron waves could have a length of 500 waves multiplied by the wavelength. So each of them could be about 75 nanometers long. These are average numbers. And so if you have a whole bunch of these and they're each 75 nanometers, how many of them can you fit in 21 microns? So this bunch can support something like 21 microns divided by 75 nanometers, around 300 microbunches. So one of these pulses coming through, and the next one after, and the next one after that, can be producing 300 little X-ray pulses. Each one of these will produce a separate X-ray pulse, okay? And they'll each be spatially coherent, and they'll each be temporally coherent for this spectral bandwidth. But their frequency, their center frequencies can fit within a broader undulator bandwidth, and that's what we're going to see. So this is some data. This is published, okay, in which they're showing here 20 consecutive shots, and this is the spectrum that they've measured. So they have crystal, the X-ray beam that comes out of the FEL goes through two crystals. It goes through one and scatters off another one. One is thin and bent so as to give a high spectral resolution, and the other one bent was only a 111 crystal, silicon 111, to give a full spectrum. So this is the full spectrum that you see, and this is 20 different consecutive shots, and you can see that the spectrum is dancing around, okay? And there are little spikes here, okay? And so this is what's shown here, okay? And this little red window is expanded below. So this is the center, the 8.3 keV that we were talking about. So you can see there's quite a spread here. And within that, you have all of these little nano spikes, okay? And there's going to be of order 300 of these spikes, likely. Something like that would be our estimate, okay? So what do so this is annoying for people who are doing spectroscopy or spectroscopy-related experiments. They'd like to get the laser light out keep the spatial coherence, but they'd like it to be in not so many spikes. So what people came up with is the idea that they would use just half of the, they got to saturation in half of the available length, which that turned out to be quite convenient. Okay, and then what they do is they put a thin diamond crystal here operating on the 004 planes, okay? And what they do is the electron bunch comes along, it's saturated, it has all those pulses we were talking about a moment ago, several hundred spikes. A magnetic field is applied that deflects the electrons around the crystal and back into the next FEL, the next half of the FEL, of the undulator structure. And the radiation itself, all those spikes go through this crystal monochromator. And it operates with a bandwidth of 1 part in 20,000. So this is also, if you look at your slides that I posted the other day, it said 2,000. That was not true. Okay. So anyway, the saturated FEL comes here. It's got a gigantic number of spikes. The radiation goes through the crystal, and all of a sudden it doesn't have a gigantic number of spikes. It's narrowed down to only those that fit within a bandwidth of 1 in 20,000. I'll show you a slide in a moment. Okay. And the electrons, which were heavily modulated, there was about 100% modulation. When they go through this little deflection system here, okay, and come back, it washes out all of their modulation. So what's coming back here is starting like the beginning of the FEL process, except that different than the beginning over here, here, as the electron bunch comes back here, it's overlapped with the radiation coming through the crystal. And so this is the seed. This is what they call self-seeded. They've used their own amplified radiation and the modulating. And so this starts out now, the FEL process starts out all over again. And remember, they only needed half of the length to get saturation. So now they're starting out, but not with the SASE, not from chaos over here. The electron bunch, all the electrons are uncorrelated, but it's driven by a relatively strong wave with a relatively narrow bandwidth and spatial coherence. So this is what's called self-seeding. And this is just some words that say the same thing. So this is about the diamond. It's a transmission monochromator. That's what they've shown here, okay? And they're showing how many undulator sections. The first 15 went in and they got to a power of 1 gigawatt. And then they went through this thing called a chicane, okay? These are magnetic fields to deflect the electrons, but the photons still go, okay? And this comes back here. And now they're down to 5 megawatts of X-ray power, but they got a long thing to go, and they amplify up again, exponential growth to 4 gigawatts. And the pulse in this case, they say, was 20 femtoseconds. And this is the bandwidth here, okay? So you see that the spectrum is going to look a lot better However, there's big intensity variations. And by the way, just in case anyone wants to read an example of an article, this article I just posted today, okay? And when we get to high harmonics, I'm going to post another 2 that you may find interesting. I posted only for those who want to look at it, but if you do, I would say my approach to getting through the literature when you have to read a lot of different things is read the title and the abstract, look at the figures, see what figures look like, and read a few of the figure captions and read the conclusion. And that should give you a gist of the article. But anyway, this article, just in case you want to look at it, is posted at the B course website. So here's the difference. The red is when the SASE process itself, this is what it looks like just before it goes into that crystal, halfway through the long FEL. And this is what it looks like after going through the crystal and being amplified again. So the output power is roughly the same in both cases, but in one of them, all of the power is within a narrow 0.4 EV. That's the one in 20,000. And in the other case, what's called SASE, it's just spread out all over the place. So they've gone from this red case, which is shown here, averaged over 20,000 shots. This spectrum, averaged over 20,000 shots, gives a 30 EV bandwidth. But this is how it looks now if you use self-seeding. Okay, and what, I wanted to say something. No, okay. How are we on time? Oh, okay, this is a good place. So is this concept clear? There's a gigantic number of pulses, several hundred pulses, X-ray pulses are coming with each electron bunch. So the electron bunches are coming at, what did we say, 120 hertz. Okay, so they're coming quickly. And they're each about 21 microns long, and they can support several hundred. So each electron bunch that's coming through can support FEL lasing of several hundred pulses within the 21 femtoseconds. Okay. By the way, you could think, I'm going to go backwards here for a second. Whoops. Suppose you were a chemist and you didn't want 20 femtoseconds. Suppose you wanted a half a femtosecond or even better. You'll see that these people accelerated physicists have a lot of tricks up their sleeve. But one of the things you could do is imagining somehow or other shortening this bunch so that it's not supporting all of these different things, okay? You just want lasing to come with one of these things, which is only has a path length of 75 nanometers, and combine that with the speed of light, and you'll have what is the pulse length of one of these things. It's really short. Okay. So for instance, in previous years, several students from chemistry did things about how to get to attosecond pulses, for instance. Okay, no comments? It's kind of understood where all of these noise is coming from. You know, this self-amplified spontaneous emission starts from noise, and it looks noisy at the end. Okay, and this is just a filter that's being applied, and if some of these pulses happen to fit into that bandwidth set by the crystal, you get a big spike. And if none of the pulses happen to fit, you don't get anything. In fact, maybe I should go back again. If one of these pulses happens to fit in the central wavelength set by that diamond crystal, you'll get a great output. But suppose the diamond crystal is set at a wavelength that none of these quite manage, maybe they just get partially through, then you're going to wind up with gigantic intensity variations, okay? So that's, so self-seeding allows you to get a narrow spectrum to do some experiments, but the pulse-to-pulse variation is pretty large, okay? So now we're going to talk about coherence properties. Okay, so I borrowed this from a scientist at Post-Tech in Korea, Sung Chang-young, and he made this nice diagram, and this has to do with them measuring using Young's double slit to measure the spatial coherence of their of undulators at their synchrotron, but also at the FEL. The PAL, I think it's called the Post-Tech, or is it called the PAL FEL? Post-Tech, yeah, Accelerator Lab, PAL. Anyway, so here's a nice diagram of the radiation coming in, the two openings, and the interference pattern here. And this is what that would look like. So this is just, I forget if this is real data. It looks real, but I'm not sure. Whoops. Okay, so we've had our diagram here, a little simpler. And what previously we were looking at was Young's double slit applied to a bunch of random electrons, and we put an aperture in front of it so that we could get good modulation. But when we did that, I don't know if I talked about it at the time, but if we looked on axis, we would see not a nice sinusoidal electric field in time, but we'd see something chaotic because we had a bunch of electrons that were radiating independently. So there would have been chaos here. So now we're going to measure the spatial coherence without a slit for the FEL, or this is what was done by this group. And this is the paper that was written. So Ivan Vatanyans led this. He was from Hamburg, the university and the lab, Daisy Lab, and it was led on our part by Anne Sakdinawat, who's the co-author on the book. And there are other names in here that just keep appearing over and over. Bill Schlatter, who's at the ALS. I think he's an author on that paper I posted. Josh Turner, Regina Souffle, who makes multi-layer mirrors, etc. And so here's the same paper, and here's the kind of interference patterns that they measured. So this was done at LCLS. It was done with the soft X-rays at 780 eV, okay? And you can see the really nice modulation that was obtained here, okay? And they estimated that it wasn't actually diffraction limited. It did not quite meet the criteria that we set for spatial coherence, but it was larger by 20%, okay? So this is what those interference patterns look like. And rather than just use Young's, let's say, double pinholes, which Young did use double pinholes, but Young also used double slits. It's just a matter of, did you have enough light to get a nice interference pattern? But Anne, who led this effort, made these structures which would measure not only for that separation, but for different separations. In fact, here's the aperture in Young's double, not double, it's a triple slit, and the separations are not the same. So there's a summation of frequencies seen, which give you information about the correlation between this distance and between this distance and between the outer distance. So you get three cracks at the coherence properties, okay? This is sort of what they look like. But I want to go back here. So this is a tough slide, but it's important concepts. And so I'll just go through 1, 2, 3, 4 and see if it makes sense at the end. So first of all, we had a point source and some angle, and we got full modulation from this point source. And when we went this way, it just depended on how many oscillations did this electron goes through. If it went through 1,000 cycles, then there'd be 1,000 in this direction, okay? And then we said, oh, well, what if we have 2 point sources? Well, then we get 2 interference patterns because these are uncorrelated with each other. So they each completely separately launching some wave fronts. Their electric fields diffract here, and then they meet. And depending on the separation of the two, there'll be a little offset in the interference pattern, okay? Because, for instance, the blue one takes a little longer to get to the top and a little less time to get to the bottom. And so they don't interfere, they don't produce a maximum right on axis, they produce a maximum shown by the dashed lines slightly off axis. And if you separate these further, you can get to the point where you just wash out all the fringes. For instance, the dashed line, if you pull this second point source down a little lower, the dashed lines fringes would move up, and you could put the peak of the dashed lines, line it up with the minimum of the solid line. You just wash out the fringes, and that would be telling us that we had a source, a combination of, if we had a combination of many electrons that set that condition, we wouldn't have any spatial coherence. We would just wash out the slides. Okay, so those are two sort of easy examples with one or two electrons. Then we look here, and maybe we didn't emphasize it a lot before, with the undulator. We have a lot of electrons in the bunch at an ALS undulator, let's say, or argon undulator. And the undulator goes, the electron bunch goes through the undulator, and each of the electrons is radiating completely independent. So the electric fields don't add except for their own electric fields. Only electric fields from a single electron will, after diffraction, interfere. The radiation from any one electron will not interfere constructively or destructively with that from any other electric field. So what happens here in the screen where you see the fringe pattern is you get this interference pattern, and as long as this lateral size of this thing is small enough, you'll have a nice interference pattern. You might have to put an aperture in front of it to get it, but you can get it. However, if you look at the electric field on axis, these electrons are all radiating at different phases. They're in a different position in the bunch, and they're moving around. And if you measure if you had a way to measure electric field and measure it fast enough, you would see a complete chaos of electric field. You're getting a nice interference pattern because you're interfering radiation only from one electron with the other. And if they're all close enough, they're all producing the same interference pattern, so it adds up nicely, you can see it. But electric field wide, it's chaos. In the FEL, evolving from the undulator at a synchrotron facility to an FEL, where this is a wave of electrons meant to be, okay, now you not only get this nice interference pattern, which we just saw was measured, but if you had the capability to measure the electric field on axis, you'd find out that all of these electrons are radiating in a way that their phases all add up on axis, and you get this very nice sinusoidal electric field. Okay.
Professor?
Yeah.
For the top left, the point source, the on-axis electric field would be also a nice sine wave like that, right? Absolutely, yeah. And then for the like slightly spread 2 point sources, it would just be like 2 sine waves added together, and the spread would determine how. Yeah, exactly. And so depending on the spread or the phase of the 2 point sources, the electric fields would show some combination of 2 frequencies. Yeah, very good.
Professor?
Yeah.
For the bottom left, when we're looking at the uncorrelated emitters, so because they're in a bunch, we say they act like sort of like a point source. So like we get these neat fringes.
Yeah.
But it's the fact that they're uncorrelated only affects the electric field modulation, nothing else.
That's right. But the intensity, which is the square of the electric field, for every one of these electrons, because it's confined to a small enough distance d that satisfied our spatial coherence condition, okay? As long as that d is small enough to satisfy this, even though there's a lot of electrons in there and they're all moving around randomly, they're all producing the same interference pattern. Every one of them has their electric fields adding in phase on axis. just separate from all of the other electrons.
Gotcha. Okay.
Yeah, okay. Okay, great. Anything else? Okay, so we have spatial coherence and we have spectral coherence because we have the grading monochromators or the self-seeding to get a narrow bandwidth, so we have a certain degree of coherence. So this is about the pursuit of sub-femtosecond X-ray pulses. So nominally they're operating the hard X-ray facilities with pulses of like 10 femtoseconds, but it could be up to 60. Sometimes you want longer pulses and more power, more photons or something. But at any rate, how could you get below a femtosecond? So this is something that really interests the FEL community. How to get hard X-ray pulses less than a femtosecond. So for lower photon energies, lower than 8 kilovolts or even lower than 1 kilovolt, if you get down to 50 eV or something, you can use laser high harmonic generation, which we'll talk about probably in a week, and that can get you well below a femtosecond. You know, so there were reports early on at 80 attosecond pulses, and now the number goes below that. But that's for photon energies in what I would call the extreme ultraviolet. Photon energies of perhaps 30 eV, 80 eV, something like that. You get a little higher into the soft X-ray regime, you can also have short pulses, but you don't have so many photons with the high harmonics. So the FEL gives you a lot of photons, but it doesn't give you the really short pulse, okay? And so there's a great interest in how to do that. So how could you do it? For example, if you had a very short electron bunch, as we were saying before, so that it only supported a single microbunch. So maybe you had a way to make that pulse not 21 microns long, but something a lot shorter, okay? That would be a way to get down below a femtosecond. Another thing which is mentioned here, some SLAC experiments where they had lasing along the 21 microns, but at the beginning, they screw up the emittance of the beam. So it was only satisfying the spatial coherence condition in a small part of the electron beam. You could just say they just screwed up the electron beam except in a narrow slice in the middle. And with that, they were able to get down below a femtosecond. So those are two ways of doing it. And here are the papers if anyone wants to take a look at it. In the one paper, they've got basically a half a femtosecond, 400 and something attoseconds. And the other paper, by bandwidth analysis, it appears by bandwidth analysis that they were able to get down to 162 attoseconds. So these are papers that are both from 2017. I haven't looked at it. I haven't noticed anything recently. Okay, but there could be something going on there.
Professor?
Yeah.
What's the application? Like, why do we want pulses that short?
It's usually, well, some sort of dynamics, but these would be dynamics, not molecular dynamics, as probably lots of colleagues in chemistry look at, but also for chemists, this would be dynamics of sort of core electrons rather than valence electrons. Yeah? So that could be material science, it could be chemistry, but it would be getting to core electrons rather than to valence electrons would be the big thing. So, some photographs. This isn't showing up. This is Sakla. This is the FEL in Japan. Okay, it's right next to the Spring 8 synchrotron, which we talked about before. The Spring 8 synchrotron is the highest energy synchrotron in the world, and they are also planning an upgrade. And when they do, I think they're going to lower the energy from 8 GeV to something a little bit lower. And actually, it's so big in diameter that they had to they had to sort of shade around this mountain. So there's a mountain in the middle of the synchrotron. Okay, and the synchrotron is called spring 8. Okay, and it has its injector and everything else, and they have a really long undulator path. But they also have the free electron laser right next to it, which they call SACLA. And so it's also producing lots of hard X-rays and lots of interesting results. And I know people from Berkeley have used it recently, just last year in chemistry, or maybe not 2020, maybe it was 2019. But many of us are there frequently. So for many, many years, I went at least once a year there, okay? And just for cultural observations, when you're trying to convince people to build billion-dollar facilities, sometimes you make certain decisions. One of the decisions that was made, I saw this myself, I was a little surprised. Before the ring was built, you know, it was partially built the first time I visited. I was shown this thing over here. Do you recognize what this is? It has a long green path over here. It's a golf course. Okay, so that's SACLA. And oh, this is interesting. So the first hard X-ray lasing at SACLA, okay, 2011. And this big ring, this is the undulator radiation. This is the this has a half angle at some great distance of 1 over gamma square root of n, and it's big. It's tens of microradians. But when the thing lasers, the angle narrows down very much because it's all coherent and it has a certain diameter and wavelength, and that sets a divergence angle. And this is what the LCLS people saw also. They had a YAG crystal, and as they were inserting more and more undulators, first of all, initially the power was increasing linearly, and then it started to exponentiate. But when it started to exponentiate, this outer ring of radiation, what they called spontaneous radiation, we would have called undulator radiation, that cone starts to narrow down. And this is what they saw that first night at Stanford, at SLAC, and this is what was recorded here, okay? And it's this is courtesy of the same guy who gave us the Young's experiment. Now this is, how are we on time? I think I'll end here and just say that when we come back, we'll talk about some experiments that they could do at SACLA that couldn't be done anyplace else at the time. And they are also having their electron beam and two sets of half of the undulators and then another half of the undulators. And then a chicane in the middle for the electron. So there's a little delay here, which they can control by how far they make this. And there'll be some, and in their case, what was special, their magnets allowed them to tune the photon energy, certain gamma. They could tune the wavelength with K. The Stanford people could not do that until recently. They had a fixed K, fixed gap. And so they could only change the energy by changing gamma. But the SACLA people from the beginning, all of their undulators were K tunable. And so we'll come back to this slide next time and to some experiments right after that where they were able to produce, and I think it's the only one that's been produced so far, an 8 kilovolt atomic laser with a really narrow line, okay? Okay, I think that's enough for today. Does anyone have anything they want to throw out there?
I guess one quick question is, do all the free electron lasers today use the self-seeding method?
Really good question. And the answer is no. We're also going to talk about using a seed, a real seed pulse. Okay, and this is the Italian free electron laser called Fermi, after Enrico Fermi, and it's in Trieste, Italy, and they start with a coherent pulse. And so we'll talk about that in the next class. We'll talk about where do they get that coherence pulse from, and why don't we use one for the X-rays? They're operating more in the extreme ultraviolet, maybe up to 100 eV. They can go higher, but their best performance is a little bit lower than that. Yeah. Okay, good question. Okay, I guess we're ready to say see you next week. Take care.
Thank you.
Thank you.
Thanks, everybody.